I am Vineet Kumar Sinha from ABES Engineering College, Ghaziabad. I welcome you all to the course which we are discussing is material engineering. And today, the topic which we are going to discuss is imperfection in solids. The syllabus which we'll cover today would be imperfections or the defects in solids, which basically will cover the point defects, the line defects, interfacial or surface defects, and also the volume defects. So as we know, as per the definition of crystalline solid, we have assumed that perfect order exists throughout the material on an atomic scale. However, such an idealized solid does not exist. All contain large number of various defects or imperfections. As a matter of fact, many of the properties of materials are profoundly sensitive to deviations from crystalline perfection. They exist because of the deviation from crystalline perfection. Otherwise, that property of material would not have exist and we could not have used that property of the material. By crystalline defect is meant the lattice irregularity. The irregularity in the lattice structure or the periodic or the orderly structure is the defect. So basically, we classify the crystal imperfections in terms of geometry or dimensionality. That is, first it is point defect, those associated with only one or two atomic positions. Second one is linear or one-dimensional defects, is having defect at a single line or in one dimension. The two dimensions are called interfacial defects or the boundary defects or the surface defects, which are two-dimensional. And similarly, the volume defects, which are three-dimensional. Where, as per the tabular form, we can see the classification of defects in crystalline as point defect, which we already discussed. In point defect, we will discuss vacancy, the interstitials, the substitutional point defects, Schottky defect, Frenkel defect. These are the defects, 4-5 defects included in the point defect. Then line defect includes two types, edge dislocation and screw dislocation. The line defects are also called dislocations. Then surface defects, where we'll have grain boundaries and twin boundaries, tilt boundary, and few more which we'll discuss. Volume defects would be having voids, the cracks, the inclusion, and the precipitate. All these are three-dimensional defects. So it is called volume defect. Coming on to first one, that is point defect. So we will start with vacancy. Because vacancy is called the basic defect, the first of the point defect. The simplest point defects is a vacancy, where any atom is missing from its regular position in the crystalline structure. All crystalline solid contain vacancies, and in fact it is not possible to create such a material that is free of these defects. It is by the definition of or the by principles of thermodynamics that the presence of vacancies are mandatory and it increases the entropy, so it can be given by the formula NV equals to N to the exponent minus QV by QT by KT, where N is the total number of atomic sites. QV is the energy required for the formation of one vacancy, create a single vacancy. T is the absolute temperature in Kelvins, and K is the Boltzmann's constant, that is 1.38 into 10 to the power 23 joules per atom Kelvin. We can have a picture where we can understand the perfect crystal is having the atoms are positioned at regular interval or regular positions. Periodic arrangement would be there. All the atoms would be having its own positions. In vacancy or the point defect, any one or more than one would be missing from its original position. So this will create a vacancy, and that is a point defect, and it is called a vacancy defect. Second one of the point defect is interstitial defect. Interstitial, what is interstitial, and interstitial, what are interstitial positions? An interstitial defect occurs when an atom takes the interstitial position of the lattice structure. So what are those interstitial positions? These positions, these spaces in between the regular position of the atom are called interstitial positions. So the interstitial defect, the interstitial atom may be of same crystal or of a foreign material. So there would be an atom at the interstitial position. So that may be of the same atom missing from some place at the crystal or any foreign material also. According to this can be classified into self-interstitial defect occurs when atom of the same crystalline solid occupies the interstitial position, or an impurity interstitial defect where atom of some other type occupies the interstitial positions. This we can have a look at here. If any atom takes the interstitial position, it can be termed as interstitial point defect. Since this is the atom of some other type, some other atom is there, so it is a impurity interstitial defect. Here we can see in this picture, since the same type of atom is taking the place of interstitial position, it may have come from some other places, then it is called self-interstitial atom. Third one is substitutional defects. Occurs when the original atom in the lattice site of a crystalline solid is replaced by a different type of atom. The regular position of the atom would be replaced by a different type of atom. For example, here we can see that this red atom is taking the regular position. It is not taking the interstitial position, and also it is not a vacancy. It is not a vacant site, but that vacancy is being filled by some other atom. But it is taking the place of regular position of the atoms where the crystal structure was having. So this is called substitutional atom point defect. Substitutional atom point defect. So it is all these three, vacancy, interstitial, and substitutional, are clear by its name only. Now coming on to point defects in ceramics. Two more defects are there which we can understand through ceramics. So both vacancies and interstitials are possible in ceramics because ceramic material contain ions of at least two kinds. Suppose NaCl is a suppose NaCl is there, Na is the interstitial vacancy and Cl interstitial vacancies may exist. In the structure, interstitial will also be there and Ci is also possible. Ci interstitials are also possible. So it is highly improbable that there would be appreciable concentration of anion, that is Cl minus interstitials, because the anions are relatively large, and to fit into the small interstitial, substantial strains on the surrounding atoms must be introduced, and conditions of electroneutrality must be maintained, and the ratio of cations to anions is not altered to maintain the electronegativity of the ceramic. So these are the conditions of having a ceramic defect. So there are two types of ceramic defects, or the defects occurred in ceramics. Those are, first one is Frankel defect. So where an atom or ion moved out of their own lattice site, making it vacant while occupying another intermediary vacant site on the crystal. This defect is also known as dislocation defect, and it also clearly depicts both vacancy and self-interstitial defects. So here we can see Frankel defect. is A plus and B minus ions are there. A plus ions and B minus ions are there because ceramics are having two types of atoms or ions or molecules. So any one, either A plus can move out from its position and take an interstitial position, or B minus can move out and take an interstitial position. And the same thing, the same Frankel that would be called Frankel defect. So both vacancy and self interstitials can be created of either of the two ions or atoms. So this is called Frankel defect. The next one defect is Schottky defect. This is called Schottky defect. When equal numbers, if equal numbers of cations and anions are missing, equal number of cations and anions are missing from the lattice, they are called Schottky defect. For example, A plus B minus ions are arranged in a regular lattice pattern or a regular crystalline pattern, periodic arrangement, in which one B minus ion is missing from this place and one A plus ion is missing from this place, as we can see. So two opposite type and same number. If two of B minus are missing, then two of A plus would be missing. So the equal number of both the ions or molecules would be missing from its place, regular place, then it is called Schottky defect. This is to maintain the electrical neutrality of the crystal will not get affected. So when equal number of cations and anions are missing from the lattice, it is called Schottky defect. So all those are for point defects, which we discussed of five types: vacancy, interstitials, substitutional, Frankel defects, and Schottky defects. Coming on to next one, that are linear defects or one-dimensional defects. Linear point defects was zero dimension. Linear defects is one dimension. So it is also called a dislocation. So linear defects are called dislocations also. It is a linear or one-dimensional defect around which some of the atoms are misaligned. Are misaligned. They are of two types. Linear dislocations or linear defects are of two types. First one is edge dislocation. If an extra portion of a plane of atoms, the edge of which terminates within the crystal, will exist with the crystal structure, then defect is known as edge dislocation. It is perpendicular to the plane of the page. Within the region around the dislocation line, there is some localized lattice distortion. The atoms above the dislocation line are squeezed together, that is compressive stress field, and those below are pulled apart, tensile stress field. So as we can see from this picture, if the atoms are arranged in a regular pattern and this, if this is considered as slip plane, if this is the slip plane from where the slip is happening or is occurring, or any dislocation or any defect is created, any defect is there in the crystal, then one extra plane, half plane would be created. One extra half plane would be created. See, if you can see here as this plane is ending here only. So this plane, this atoms are in linear configuration. This is linear configuration. This is linear configuration. And this would be connected with this, but now an extra half plane is created, and for this there is no plane, no number of atoms in the bottom plane. So this extra half plane would be created, then it is called a edge dislocation, and the line of dislocation would be inside the screen or inside the paper, inside the plane of the paper or inside the plane of the screen, if you can imagine. This extra half plane is along and is ending along the inside of the screen. So this type of dislocation is called edge dislocation, and in the upper half, the lines are squeezed together and create a compressive stress field, and the lines below could create a tensile stress field. The magnitude of this distortion decreases with distance away from the dislocation line. As we move along, as we move beyond the dislocation line, means as we move up, the intensity of compressive stress field will decrease, and as we move down here, then the magnitude of the tensile stress field will reduce. It is represented by this symbol when extra half plane exists in upper half, as in this case, and by this symbol when extra half plane exists in lower half. Here also we'll be able to see the edge dislocation. How is it happening? The extra half plane is ending here. This half plane is ending. Now no bonding with next atoms. So these atoms will bond together with each other, and this will bond with this one. And an extra half plane would be created, and the dislocation one line would be inside the plane of the paper or inside the plane of the screen. So edge dislocation is called edge dislocation. The second type of linear dislocations or linear defects are called screw dislocation. What is it? When shear stress is applied to produce the distortion such that the upper front region of the crystal is shifted one atomic distance to the right relative to the bottom portion. Here we can see that this is the motion would be of screw type. Screw, as we open or shut the screw, this is moving. The movement is, the dislocation is of screw type. So atomic distortion associated with a screw dislocation is also linear and along a dislocation line that is parallel to plane of the page. Here the dislocation line would be something like this, and hence the dislocation line would be parallel to the plane of page or the parallel to the plane of screen. The symbol used to designate a screw dislocation is like a screw. This symbol. Most dislocations found in crystalline materials are probably or neither pure edge or nor pure screw, but exhibit components of both types. These are termed mixed dislocations. So, edge dislocation, screw dislocations, and also mixed dislocation. Coming on to Berger vector, since we are discussing with linear defects or linear dislocations, Berger vector plays an important role. It is the magnitude and direction of the lattice distortion. It is distorting here. It is distorting here. This. The atoms are distorting in this line. So the lattice distortion associated with a dislocation is expressed in terms of a Berger's vector denoted by B. Denoted by B or like this. Since it's a vector, it is denoted like a B and vector symbol. The nature of dislocation, that is edge, screw or mixed, as we discussed above, is defined by the relative orientations of dislocation line and Berger's vector. Here in this case, the Berger vector is in this direction, and the line of dislocation is also in this line. This what we had seen earlier. So this is parallel to each other. So the relative orientation of dislocation line and Berger's vector gives the whether it is a edge dislocation or whether it is a screw dislocation. For an edge dislocation, they are perpendicular, whereas for a screw, they are parallel. For an edge, they are perpendicular, whereas for an screw dislocation, they are parallel. Here we can see, since this is a screw dislocation, the Berger vector is in this direction and dislocation line is or the vector is in this direction. So both are parallel to each other. So this is an screw dislocation. What we saw previously, here the Berger vector is in this direction, means the moment is in this direction, slip is in this direction, and the dislocation line would be inside the inside the screen or perpendicular to the screen plane of the page or plane of the plane of the screen. So this is perpendicular to each other. So this is called edge dislocation. So in terms of Berger vector and dislocation line or dislocation vector or tangent vector, it is also called tangent vector. We can mention the whether it is a edge dislocation or it is a screw dislocation. We can have a look and more understanding from this picture. Suppose this is a picture of perfect crystal. This is perfect crystal. Here all the atoms are placed periodically. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if we take a Berger circuit, if we try to complete a circuit starting from this point, we'll move one atomic distance away. 1, 2, 3, 4, 5, 6, and 7. Similarly, we will try to complete a circuit. 1, 2, 3, 4, 5, 6, and 7. Similarly, 1, 2, 3, 4, 5, 6, and 7. And also then to complete the circuit, 1, 2, 3, 4, 5, 6, and 7. So for a perfect crystal, we can see that when we move along the atomic distances and try to complete a circuit, we'll reach at the same point, same starting point, and there would be no gap. But for an edge dislocation or for any linear dislocation, suppose this is an edge dislocation where this extra half plane is created and rest atoms are bonded with each other because of this extra defect or the edge dislocation. Here, if we try to start from this point and try to complete a Berger circuit, we'll move one distance 1, 2, 3, 4, 5, 6, 7. Then we'll go down 1, 2, 3, 4, 5, 6, 7. Then again 1, 2, 3, 4, 5, 6, 7. And again 1, 2, 3, 4, 5, 6, and 7. But here we can see that will not reach to the similar start position. The finish position is different from the start position. Why is it so? Because this is the slip plane. This is the slip plane from where this slip is occurring. And it is creating or a defect has been created, that is extra half plane. Extra half plane. And this is, as per the definition, is called the edge dislocation, for which the corresponding atoms are not available in the opposite side of the slip plane. So if we take a Berger vectors around the dislocation across the slip plane, will not reach at the same position what we intend to in the first place. So there is a convention, many conventions are there, but generally being followed is the right hand finish to start convention. Right hand finish to start convention states that if we start in the right direction, if we take a Burgess vector in the right direction, starting towards right, 1, 2, 3, 4 subsequently, and try to complete a circuit like this, what we did, then finish to start. Finish to start would be the Berger vector. Finish to start. So one atomic distance away, finish to start is in this direction. Finish to start is in this direction. So this is the Berger vector. So Berger vector is in this direction for this particular case, and the dislocation line here in this picture we can see that was the slip plane. This is the direction of Berger vector which we derived from this place, and this is the dislocation line. Dislocation line is, as for edge dislocation we already discussed, it is inside the plane of the paper or inside the plane of the screen. So dislocation line is also called T vector, tangent vector, or dislocation line vector. So the relative position of Berger vector B, the relative position of this Berger vector B and this T is defined the whether it is edge dislocation or screw dislocation. Since they are now here in this case they are perpendicular to each other, so it is a edge dislocation. So if we tabulate the relative uh, aspect of these two edge dislocation and screw dislocation, we can have the dislocation property, that is relation between dislocation line T and B. So for an edge dislocation, it is perpendicular to each other. For a screw dislocation, it is parallel to each other. Slip direction, the direction of the slip is parallel to Berger vector. Here it is also in screw dislocation also, it is parallel to Berger vector. Means the Berger vector is in this direction and slip direction is also in this slip. This is slip direction because the force is acting, the shear force is acting in this direction only. So this is parallel to each other. Similarly for screw dislocation also, since Berger vector is like this and also slip is in this direction only. We are applying the force in this direction only. So parallel to each other in this case also. So if we tabulate the processes, then this slip direction is parallel to B in this case also and parallel to B in screw dislocation also. Another criteria is direction of dislocation line movement relative to B. Dislocation of Direction of dislocation line movement related to B. Here it is parallel and here it is perpendicular. And process by which dislocation may leave slip plane, it is climb and cross slip. Coming on to after linear defects, coming on to interfacial defects or the surface defects. Interfacial defects are two-dimension defects and normally separate regions of the materials that have different crystal structures and or crystallographic orientations. So the first type of surface defect is external surfaces. We all know that one of the most obvious boundaries of any surface of any material is external surface, along which the crystal structure terminates. And at the end, the external boundaries, the external surface boundary. The surface atoms are not bonded to the maximum number of nearest neighbors and therefore in a higher energy state. The atoms lie in a higher energy state than the atoms at interior positions, and the bond of these surface atoms that are not satisfied give rise to surface energy, and to reduce this energy, materials tend to minimize the total surface area and a defect is created. Second type is grain boundaries. The boundaries of the grain are the defect points or the defects in the crystal. Within the boundary region, which is probably just several atoms distances wide, several atom distances wide are the grain boundaries. One grain is having several atom is consists of several atoms. There is some atomic mismatch in a transition from the crystalline orientation of one grain to that of adjacent one. So the orientation, crystalline orientation gets changed when the boundary change or the grain when the atom will cross from one boundary to other. Various degree of crystallographic misalignment between adjacent grains are possible, and according to which, if the mismatch is slight or the angle of the mismatch is, the angle of deviation is less than 10 degree, it is called low angle grain boundary or small angle grain boundary. And if it is greater than 10 degrees, more or less 10 degrees, then it is called high angle or high angle grain boundary. This type is called a tilt boundary. So here we can see the grain boundaries. Suppose suppose these are the grain boundaries. These lines are grain boundaries. This line is a grain boundary, and also okay. So here, if we take this line, the atoms were in this line, and now here it changes position to this line. So the misalignment is, it would be like this, but now it is like this. So the misalignment would be this angle. If this angle is less than 10 degree, it is called small angle grain boundary defect. Or if it is greater than 10 degree, it would be called high angle boundary defect. Here in this case, this was moving in this line, was arranged, this item was arranged in this line, and here it takes this line. So the angle is higher, and so this is high angle grain boundary, and this is low angle grain boundary. And this is called angle of misalignment also. Tilt boundary is a type of surface defect or interfacial defect. Here is a type of crystallographic defect or boundary that occurs when two regions of a crystal lattice are misaligned with respect to each other along a specific crystallographic direction. They are misaligned. All the grains are misaligned according to a specific crystallographic direction. Suppose this for having a edge dislocation here, and so there would be a dislocation, a change in the boundary here. Again, same dislocation and change boundary. So overall, there would be a angle associated with a specific angle associated with the grain boundary, and this is called a tilt boundary, having a tilt angle theta. Similarly, twin boundaries, it may have a defect of twin boundary. Twin boundaries, what is a twin boundary? It is a spatial type of grain boundary across which there is a specific mirror lattice symmetry. It's a mirror image of one side to the other. We can see here from this picture, there's the same distance located, and in this atom is located at same distance and at the same orientation, and the mirror image of this left side is having the mirror image of the right side or the vice versa. So twin results from atomic displacements that are produced from applied mechanical shear forces. Similarly, the other defects in this surface defects or interfacial defects are stack fault, which is a interruption in the stacking sequence of the FCC metals, generally occurred in FCC metals, that is ABC, 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 which we discussed earlier during the FCC. This is the stacking sequence. When there is a change in stacking sequence of closed packed planes, this is called stack fault. Similarly, phase boundaries may exist, and it's also a type of defect of surface defect, where the multi-phase materials across which there is a sudden change in physical and or chemical characteristic due to different occurrence of different phases. This is called phase boundary. Now coming on to the last segment of defects, those are volume defects. Volume defects or three-dimensional defects. 3D defects. Volume defects in crystalline solids are three-dimensional imperfections that occur over a significant region within the crystal. These defects involve irregularities that span across multiple atomic layers. It is not associated with one or two atoms or one or two atomic layers, multiple atomic layers in three dimensions and affect the material bulk properties. Volume defects are often caused by impurities, voids, or secondary phases that are introduced during the manufacturing process. How this defect is created, the volume defects are created in the crystal during manufacture process or arise from material degradation over time. Some common types of these defects, volume defects include, first one is voids. Voids. These are empty spaces or cavities within the crystal where atoms are missing. Atoms are missing from its place and not one or two atoms or a 10 to 15. It's a n number of atoms, which is creating a 3D missing empty spaces or cavities. They can form due to processes like solidification, manufacturing process or solidification, shrinkage, radiation damage, or plastic deformation. These are the causes of having the creation of voids. Voids act as stress concentrators. If we all know that if a void is created on a material surface, then the stress would be concentrate on that. So stress they are stress concentrators, making the materials more prone to failure under stress. That is fracture or crack propagation. Voids can also reduce the material's density and strength. The other type of volume defects is precipitates. What are precipitates? These are small solid particles of a different phase. Solid particles of a different phase that form within the host material. They often result from the limited solubility of alloying elements. They have the limited solubility of alloying elements, which leads to the formation of distinct phases upon cooling or heat treatment. They are not having unlimited solid solubility. They are having limited solubility. So while cooling or heat treatment, the different phases gets created and the precipitation of the other phase happens, and this is called precipitate defect. Precipitate can strengthen materials by blocking dislocation motion. That is called precipitation hardening. This is an advantage to us. This is a type of advantage which we use in our general applications. They strengthen the material through blocking dislocation motion also, that we'll study later. However, too large or incoherent precipitates may weaken the material by creating weak points or stress concentrations. Third type of volume defects are inclusions. Inclusions means the foreign particles, addition or inclusion of foreign particles or impurities that become trapped within the crystal during the material's formation. These can be non-metallic impurities like oxides, sulfides, or carbides. Inclusions typically act as stress concentrators, reducing the ductility and toughness of the material. In some cases, controlled inclusions can enhance properties such as machinability, and that is adding lead in steel. Fourth type of defect, volume defects, are cracks. Cracks are large fractures or separations within the material formed due to mechanical overload. If mechanical overload happens, the cracks get generated. We all know thermal stresses. Due to thermal stress also, the cracks get generated on propagate, or the propagation of smaller defects like void or inclusion, which we discussed earlier. The smaller defects like void or inclusion, if they propagate, they create a crack. Cracks significantly reduce the material's load bearing capacity. making it prone to catastrophic failure under stress. So we must avoid this. The generation of these cracks or the defect of this crack is very dangerous. Cracks can also serve as initiation points for further damage such as fatigue failure or corrosion. They may influence the increase in fatigue failure or corrosion. So these cracks must be avoided. The fifth type of volume defect are second phase particles. Second phase particles are regions where a different phase exists. And two phases or different phases exist. Those regions are the second phase particles. Those are called second phase particles. This phase can have different mechanical, electrical, or thermal properties compared to the matrix. Second phase particles can either enhance or reduce the material mechanical property depending on their size, shape, and distribution. In composite materials, second phase particles like fibers or whiskers are intentionally added. The reinforced materials, the reinforcement which we intentionally add to improve properties like strength, stiffness, or wear resistance. So in composite materials, we intentionally use second phase particles to improve their properties, mechanical properties like strength, stiffness, or wear resistance. Similarly, the last one of the volume defects are pores. These are similar to void, but are typically the result of incomplete densification or during the material fabrication, or particularly in ceramics or powdered metallurgy processes. So particularly in ceramics and powder metallurgy process, these are called pores in place of voids. Pores reduces the mechanical strength and toughness of the material. They can also impair properties like thermal conductivity by corrosion resistance by increasing surface area and allowing more chemical attack. So this is also a type of defect which needs attention and must be avoided. So that was all about the imperfections or defects in solids, which we discussed in detail. Those were point defects, the linear defects, line defects, or the surface or interfacial defects, and also the volume defects. So this is the discussion. We should end here, and subsequently we'll discuss in next video. Thank you.